Hi everyone! Today we'll be solving an easy linked list question. Given the head of a linked list, decide if there is a cycle in it. We'll cover two solutions in Go, one with ON and one with O1 space complexity. Let's get started! First, a more intuitive and straightforward approach. We use a map to store if we have encountered the list node before. Starting from the head of the linked list, if the current node is not present in the map, we put it in and set the value to true. Now we iterate through the map, and each time we use the current node as the key to check the map and initialize the value. In this example, when we reach the final node 4 and we check the next value 2, we realize that it is already present in the map with the value set to true. This means that we have passed by this node before and there is a cycle in the linked list. Now, if we look at this other example of a linked list with two elements, for every node in the list, we are initializing a new key value pair in the map. This means that there are no nodes which are present as existing keys, and there is no cycle in the linked list. Hence, by using a map, we have successfully determined whether there is a cycle in the linked list. And this solution takes ON time complexity because we are traversing the linked list only once, and ON space complexity because we are using a map to store the n elements in the linked list. Let's code it out. First, initialize a map of a list node to has encountered Boolean. Now, we start from the head of the linked list. As long as there is still a next list node, we want to iterate through the linked list. And first, we check if the current list node is present in the map. If it is, it tells us that we have encountered this node before, and hence there is a cycle in the linked list. So we return true. Otherwise, we want to set this list node as the key in the map and set the value to true to show that we have encountered this node before, and we move the pointer to the next node. And if we iterate through the whole linked list and none of the nodes we have encountered before, we know there is no cycle in this linked list and hence return false. There is one more edge case we need to check for, which is if it is an empty linked list, there is no cycle, we just return false, and there is no need to go through the loop. There we have it. Now, can we do better? Let's take a look at another approach which uses constant memory with two pointers. We reuse the same example as before and start with a slow pointer and a fast pointer. The idea is the fast pointer always moves twice as fast as the slow pointer. So let's visualize. First, the fast pointer moves 2 spaces from 3 to 0. At the same time, the slow pointer moves 1 space to 2. And in the next iteration, the fast pointer moves from 0 to 4 and then to 2 again. And at the same time, the slow pointer moves 1 space to 0. Finally, the fast pointer moves 1 space, 2 space to 4, and the slow pointer moves 1 space to 4. So here, we see we have met again at 4. Since the slow pointer eventually catches up with the fast pointer, we know that there is a cycle in this linked list. Let's take a look at another example. Again, we start with a slow pointer and a fast pointer at the head of the linked list. First, the fast pointer moves 2 spaces to 3, and the slow pointer moves 1 space to 2. Now, the fast pointer has nowhere to move, because there is no next node for the fast pointer to reference. And hence, we have come to the end of the loop, and the slow pointer does not meet the fast pointer. Hence, we know that in this case, there is no cycle in the linked list. This approach is also called the Tortoise-Hare Algorithm, or Floyd's cycle finding algorithm. It allows us to determine if there is a cycle with O1 space complexity, because we're not using any other data structure to store the elements of the linked list. Now, let's code out the solution. First, we initialize both the slow pointer and fast pointer to the head of the linked list. And as long as there are still elements to check for the fast pointer, and it has not reached the end of the linked list, we want to iterate through the list. Each time, we set the slow pointer forward 1 index, and the fast pointer we wanted to move twice as fast as the slow pointer, so we set it to 2 indexes forward. If at any point in time the fast pointer catches up to the slow pointer, that means there is a loop in the list, so we return true. Otherwise, if we go through the entire linked list and none of the pointers match, it means there is no loop, so we return false. There we have it.